Let's use our substitution for double integrals theorem for the first time here. And so what we want to do is to, let's see here, use change of variables to evaluate the double integral over d of e to the x minus y dA. D is the parallelogram spanned by these two vectors here. What do I mean by this by this parallelogram? So let us draw a picture here. So 1, 2, 3, 4, 1, 2, 3, -1. Okay, so 1 point here. So the vector 4, -1. Okay, there's that vector. And the vector 2, 3. There's that vector. And then we finish this off. Finish off our parallelogram by drawing that, translate those vectors over here. And so it looks like this. So this is the region D that we want to integrate this over. So first off, let's just realize that we could do this using, early in chapter 15 techniques. We could, but it would require slicing it into one. I think we'd have to slice into 3 parts there. One part for that as a top function, that for the bottom function, one integral, one double integral for that as the top and that as the bottom, and a third one, that as the top, that as the bottom. That sounds like a lot of work. So instead, something that we should realize here is that every parallelogram like this we can obtain from, so let's see here, I'm just going to label this that, we're integrating in the xy plane, but instead every parallelogram like this with a vertex at the origin we can get to by a nice linear map from the UV plane, mapping the unit square 0, 1 over here. And the way that we do that is we're going to set, x and y. X is going to equal 4u plus 2v. How did I come up with 4u plus 2v? That's the x components of these two vectors here. And y is going to equal -u plus 3v. How do we come up with -u and -1 and 3? Well, -1 and 3 right there. But let's just check this. Of course, we should know that linear maps send straight line segments to straight line segments here. When u and v are 0, 0, plop in 0, 0, x is 4 times 0 plus 2 times 0 is 0. So y is -0 plus 3 times 0 is 0. So 0, 0 gets sent to this point right here. When u is 1 and v is 0, x is 4 times 1 plus 2 times 0 is 4. Y is -1 plus 3 times 0 is -1. So this point gets sent right there. What else should we do? When u is 0 and v is 1, x is 4 times 0 plus 2 times 1 is 2. Y is -0 plus 3 times 1 is 3. So 0, 1 gets sent to 2. 3, I'll let you check for yourself that 1, 1 gets sent to, I guess that is 6, 2. Okay, so going back here, we see that, so R is the nasty region. So the double integral, okay, here I'm using D here. The double integral over the nasty region of f of xy dx dy is equal to, okay, what do we have to do here? We integrate in the UV plane over the nice region. I think we can agree that this is a lot nicer region to integrate over. F of, okay, so we do the substitution. We replace x and y with these in terms of u and v. We multiply in by the Jacobian, and then we evaluate. Okay, so what do we have to do here? Well, let's calculate the Jacobian. So the Jacobian, in terms of uv, is going to be, let's see here, partial derivative x with respect to u is 4. Partial derivative x with respect to v is 2. Partial derivative y with respect to u is -1. Partial derivative y with respect to v is 3. So this is going to be 4 times 3 is 12 minus 2 times -1. So that should be 12 plus 2 is 14. Okay, so this is the Jacobian here. So now the double integral over region D of e to the x minus y dA is equal to the double integral over this nicer region here, which is uv both run from 0 to 1, of e to the x minus y. X minus y, well, x is 4u plus 2v. And y is -u plus 3v. And then we multiply in by the Jacobian. You know, this notation and this notation both mean the Jacobian. Multiply by 14 dv du. Okay, and so this should be a relatively straightforward double integral to evaluate. Okay, e to this expression here becomes e to the 5u minus v times 14 dv du. We can actually rewrite this e to the 5u plus v. This is e to the 5u times e to the -v. So this factors here. We move the constant outside the integral. 14 times the integral from u to u is equal to 0 to 1 of e to the 5u du times integral v from 0 to 1 e to the -v dv. And what do we end up with? Antiderivative e to the 5u will be 1/5 e to the 5u. Plug in u from 0 to 1. Times, antiderivative this will be -e to the -v, plug in v from 0 to 1, and this will be 14 times 1/5 times e to the 5th minus e to the 0 will be 1 times -1 times, let's see here, e to the -1st power minus 1. Okay, and so this is our first example of applying this general substitution for double integrals theorem.